Good afternoon, and welcome to this special roundtable called Towards Renewable Energy Storage in the Seas. This is a follow-up roundtable to the one hosted by the ALPHEUS project almost a year ago to the day. That was on 16 March 2023 that I had the pleasure of moderating as well. Congratulations to the coordinator of ALPHEUS, Roelof Mol, for getting the organization almost exactly to the day. Impressive. So my name is Stuart Ragluth. I'm the founder of Revolve, a media group dedicated to communicating sustainability, and I'll be your moderator today again. So when we think of hydropower storage, we think of rivers and what's called high head hydro, that is from reservoirs in the mountains. I'm told that over 95% of global stored energy comes from pumped hydro, which is an impressive fact. The lesser known, but equally important and arguably more interesting hydropower storage technology is called low head hydro, which is from lower areas such as the sea. The ALPHEUS project is looking particularly at the potential for low head in the North Sea region. We're going to hear about that more about this on this panel roundtable today. Currently, there's 0% of global energy storage coming from low head. So figuratively, the only way is up, as the expression goes. Today, we will learn more about the technological advances being made, the market conditions, and future perspectives for the implementation of low-head pumped hydropower. So we're going to start with a presentation by Dr. Jeremy Bricker, the scientific coordinator of ALPHEUS at TU Delft, followed by interventions from Mrs. Bettina Geisler from Geisler Law, Dr. Peter Hoffman, director of TenneT, Mrs. Anne Overmeyer, director of Blau Cluster, and Mr. Anton Schleiss, who has previously been involved with Hydropower Europe and ETIP Hydro. So for the audience watching, the attendees, you're welcome to drop your comments and questions in the chat, and I will do my best to loop you into the discussion after the initial interventions from our panelists. So let us begin with Jeremy. Please, the floor is yours. I believe you have some slides and a presentation of some 10-15 minutes.
Thank you. That is correct. Is my screen visible?
Yes.
Thank you. So, right, I'm Jeremy, the scientific coordinator of ALPHEUS. I'm going to introduce the project to you. So ALPHEUS is funded by the European Union's Horizon 2020 program. The consortium members are all over the EU, led by TU Delft in the Netherlands. And the purpose of the program is to develop civil, mechanical, and electrical technologies to make pumped hydro storage economically viable in shallow seas and in coastal environments with flat topography, like the Low Countries. This shows you our partners, TU Delft, IHE Delft, TU Braunschweig, University of Po, Uppsala, University of Tuschia, Advanced Design Technology, Chalmers, NTNU, Stuttgart, and Uni Gent. As Stuart said, most energy storage worldwide is pumped hydro, but it's only feasible in areas with large topographic differences in the mountains, high and medium heads. Our project strives to make it practical and economic for low countries as well, where natural topographic differences don't exist. And this schematic on the right here shows you the general idea. The sea on the right, or the ocean, and a lagoon surrounded by a ring dam on the left. When there is extra power in the power grid, like at night, water is pumped out of the basin, lowering the inner water level. And when there's peak power needed in the grid during the daytime, ocean water or seawater flows back in through turbines to generate power. This schematic shows a similar thing. Once again, a dam that encloses part of the sea in a ring, and a reversible pump turbine, which during the nighttime, this red line shown here, pumps water out of the reservoir draining it down during the daytime, for example, when there is peak power needed in the grid, allows water to flow back in through a turbine, thereby generating electricity. And the scale that we've been developing this at prototype scale is a 2 gigawatt facility for 10 hours at full capacity, so 20 gigawatt hours. Our project has identified feasible sites for this technology in the North Sea. As you can see here, sites in the Dutch North Sea, co-located with planned wind farms, in the English Channel, shallow regions of the English Channel near France, the German North Sea, also the Belgian and Danish North Sea coasts, not shown on this slide. The general civil technology consists of a concrete caisson dam, this on the left being the sea, buttressed by an earthen berm, on the right being the lagoon, with a powerhouse section itself consisting of modular caissons that are floated in, prefabricated and floated in, with power conduits and reversible pump turbines and machine halls inside them. The reversible pump turbine technology itself at prototype scale consists of a counter-rotating or contra-rotating propeller. That means there are two propellers, rotor 1 and rotor 2, each of which are attached to a bulb. Another concept has them concentric, using one bulb, but this is the two bulb concept, where the electrical machines for each rotor are in a bulb. Those electrical machines are axial flux, permanent magnet synchronous machines, which I will show you more information about in a bit. But what's really unique about this is that the presence of two rotors allows, well, during pump mode, axial flow to be generated without much swirl in the flow. So energy is not wasted on generating swirl in the flow. It remains axial. One prop, the first prop generates swirl. The second prop reduces the swirl, and turns it into axial flow. And similarly, during turbine mode, swirl that is induced by the first prop is used by the second prop to generate power. So it's a highly efficient technology in both pump and turbine modes. So how are we evaluating this? We're at model scale. We are measuring the performance of this device in the laboratory. And here is a video by TU Braunschweig showing how we do that. So as discussed before, we have pump and turbine modes. And the way that we are evaluating this in the laboratory is that we have an elevated tank representing the sea and a lower tank representing the inner basin. And we can flow water from the upper tank to the lower tank to measure performance as a turbine. Let me go back a sec. And pump water from the lower tank back to the upper tank to measure performance as a pump. This shows the elevated tank, penstocks coming down to the lower tank, a butterfly valve used for throttling the flow and control, transformer flow measurement, motor controllers, and our actual turbine attached to a lower tank. This shows the way our water flows in both modes. Here in turbine mode is water upwelling from the device, shown here, into the lower tank. Here you can see the counter-rotating prop spinning through this acrylic test section, driving two motor generators. Each of the props can spin at different speeds, controlled separately. Flowing into the lower tank, our model generates up to 400 liters a second. Once again, this is model scale, not prototype scale. We make many measurements in the laboratory, and again, we are running up to 8 meters of head, a realistic head, in the laboratory. This is our data acquisition system. And if experiments show in turbine mode, model scale efficiencies up to 82%. This video here is showing the propellers being pushed by the flow when the lower tank is filling. These are not being operated by motors. You do see cavitation. This is not set at a low enough elevation to prevent that. At prototype scale, this is designed to be set at a low enough elevation to prevent cavitation. In turbine mode, we're seeing efficiencies up to 92%. Once again, at model scale. So here you see the motors driving the pump flow. And that shows our mechanical device. Now I will introduce our electrical device. Oh, wrong video, I'm sorry. I need to ask, can you hear the audio to this?
Super.
Stuart? Sorry?
Sehr gut, super.
Good, thank you.
Jeremy, if there is audio that goes with this video, we cannot hear it.
You cannot hear this. You cannot hear the audio.
We cannot. We can see it.
Okay,
Yeah.
so I guess Zoom does not support that. So in which case I can narrate instead.
Mm-hmm.
So this is another concept for the prototype scale contra-rotating propeller in a bulb. Instead of having two separate bulbs, both machines are attached to one bulb to their electrical machines via a concentric shaft. So this is what the axial flux machine looks like. It has stators and stator and a rotor, which instead of being concentric with each other, are along the same axis. So the flux moves along the axis instead of radial. This allows a more compact machine and allows multiple machines to be stacked on each other. So let's see, I'll move down the video. This shows these machines running in the laboratory in Ghent. Oops, I'm sorry. So the electrical machines, once again at model scale, have efficiencies about 95%. And they are currently being driven and driving induction motors. In the next month, the project is hauling these electrical machines to Braunschweig to replace the induction motors in Braunschweig with these. So we have a full turbine and PTO together. So this is done at UKent by the people listed on the top right here. I'm sorry the audio did not work out. And let me continue then. So that introduced our turbine and electrical machine technologies developed by the project. Designs existing at prototype scale and being tested in the laboratory now at model scale, but against realistic heads up to 10 meters. So our analysis of the technologies in the project, primarily the civil structures, has shown costs. So for a project of 2 gigawatt capacity, operating for 10 hours, so 20 gigawatt hours of storage, with a lifetime, assuming 100 years, a discount rate of 5%, and an assumed round trip efficiency of 70%, though we get slightly higher than that at prototype scale, assuming all losses. We have calculated O&M costs of $117 million a year, a capex of $5.5 billion, leading to a levelized cost of storage of about 5.5 billion euros, and levelized cost of storage approximately 190 to 200 euros per megawatt hour. What we see here in this chart is that levelized cost of storage is on the high end of conventional or mountain pumped hydro storage. And that's not surprising because we need to do a lot more work to generate the head available by building a large dam. But it's not much more than most conventional pumped hydro storage projects. We also see our levelized cost of storage is on the low end of lithium-ion batteries and hydrogen. Our global warming potential is similar to the other technologies, and our use of minerals and metals, our abiotic depletion potential, is much lower than what batteries entail. So revenues can be obtained from multiple uses, multiple timescales, longer timescales, day ahead and intraday. At shorter timescales, frequency restoration reserve and frequency containment reserve. And what we see in this plot here is how prices vary for frequency containment reserve, showing for just that green part, the frequency containment reserve, a revenue of about 100,000 euros per megawatt generated, or per megawatt installed per year. So our conclusions are that, one, the North Sea has plentiful sites for low-head offshore pumped hydro storage. Civil technologies are already well developed and mature. Dredging and offshore companies around the North Sea already know how to build with caissons and embankments. Electromechanical technologies have been fully developed and are being tested at model scale. And at prototype scale, designs show efficiencies up to 80% round trip. Total round trip efficiency, which includes civil structure losses, valve losses, and also trash rack and fish screen losses, still greater than 70%. Our levelized cost of storage is at the high end of conventional pumped hydro storage, but the low end of lithium ion. Our abiotic depletion potential is much lower than that of lithium ion, similar to global warming potential, similar to lithium ion. And we can generate revenues for grid balancing on timescales from minutes to days. So that is all for my presentation. I thank you for your attention, and I will stop sharing.